Welcome to our next section of physics. This chapter we will be studying momentum and impulse. And in order to do that, first we need to look at two different types of collisions. The first type of collision is called inelastic. And what that means is the colliding objects are going to become coupled or tangled together. You're going to see this before and after picture scenario set up and used quite a bit. So what it's representing is before a collision, this is when the collision occurs, and this would be afterwards, so what the objects look like after they have collided. If the collision is inelastic, you will have two separate vehicles. I happen to say that this first one is going to be at rest, and this other one is moving towards it with some sort of velocity. If the collision is inelastic, then those objects are going to become coupled or tangled together. So what I did was I just kind of made this crumpled little mass. So we know that they're going to stick together and they're going to move off as one big mass. So the masses combine to form one object. Do you think that this one big mass would be faster or slower than this first car's original velocity? Well, if you look at the picture, or if you think about it, if something has a larger mass, it's going to move more slowly, and I also indicated that with a smaller velocity vector. And I indicated that it's v final, so I put an F for a subscript to let you know that that's going to be the final velocity after they've collided. The second type of collision is called elastic collision, and this occurs when the objects collide without lasting deformation or the generation of heat. Now this phrase, without lasting deformation, that means that the object might be able to squish a little. So if you were to throw a bouncy ball on the floor, it will compress just a little bit, but once that collision has occurred, it's going to return back to its original shape. Also, there's no generation of heat, so we're not having any sort of friction or anything like that that's going to occur with an elastic collision. So I have a couple of examples for you. So for this first one, I color-coded my objects that are going to collide. I had the first one start out at rest, and the other one is going to be moving toward it with some sort of velocity. Once they collide, I assumed that the objects have the same mass, so I drew them the same size in the picture. Now my first object that was moving, after it hits its second object and collides, now it's going to be still. And my green object that was initially at rest, it's now going to take on the same velocity that the first one had initially. So if two objects have the same mass and one of them's at rest and the other one comes and hits it, you can think of them as simply transferring their velocities from one to the other. And remember that velocity is a vector quantity, so we could also have a scenario where the objects are moving toward each other. So I have my blue object moving in this direction, and the green one is in the opposite direction. So then they're going to collide, so that's my middle line between my before and after. And after the collision, notice that they change directions. So in this particular instance, they kept the same velocity, it just switched from going one way to the other way. So they would come toward each other and then bounce off and rebound, so to speak. And my third example has the objects hitting each other but at different velocities. So my first one is going really slow, and then the second one comes along and hits it rather quickly. So it has a large velocity and it catches up to this one. Once they have collided, the first object is going to slow down and the second one is going to speed up. A really common case that you might see would be in billiards or pool. Those particular pool balls or billiard balls, like the 8-ball or the cue ball, they are as close to a real-world, perfectly elastic scenario as you're going to get. So if something undergoes an elastic collision, you want to think of the object as bouncing and hitting off of each other. So an easy summary would be inelastic collisions, the objects stick together. Elastic collisions, the objects bounce off each other. Now I know that's not a perfect description, but it is a pretty easy way to distinguish between the two types of collisions. Next, we're going to define and come up with formulas for momentum and impulse. This particular section is just an introduction, but later on in the chapter, we're going to look at our two different types of collisions and see how the momentum and impulse changes for our different objects after they've collided. But let's start with the basics. Momentum is simply the product of the mass and the velocity of an object. And this is one of those nice scenarios where the definition for a vocabulary term happens to be the equation written out in words. So momentum is going to be indicated with a lowercase p, and I hope you remember back from chapter 1 the difference between scalar and vector quantities. This arrow indicated over the variable lets us know that it is a vector quantity, so the direction is going to be important. Now p is for momentum, and that's going to be equal to, and the definition told us that it's the product of the mass and the velocity, so we're simply going to multiply those two things together, mass times velocity. As for the units, mass is measured in kilograms, and then velocity would be measured in meters per second. And what we do is combine this. There's no shortcut to the units. You're just going to have to write out kilograms times meters over seconds. So let's take a moment and go back to Isaac Newton when we talked about forces and relate this to momentum. So Newton had said that the force of an object is the rate of change in momentum. When we talked about forces before, we were looking at a mass times an acceleration. This time we're going to look at a rate of change in momentum. So let's see what that looks like. We would simply say that the force is equal to, whenever you see this word rate, that means divide by time, and then a change you should know is indicated by the delta symbol, and then of momentum is going to be our p. So change in momentum over time. I'm going to make a substitution, and momentum is the mass times the velocity. However, mass doesn't really change when an object is traveling, but its velocity can. So I pulled the m out and just said change in velocity over time. Hopefully you're going to recognize change in velocity over time. That should look really familiar to you. If it doesn't, you want to think back to Newton's second law and recognize that the change in velocity over the time is equal to an object's acceleration. So when we multiply that by the mass, we actually end up with Newton's second law of force was mass times acceleration. But now we have another way to state it. Now we can think of it as a rate of an object's change in momentum. And it's this change in momentum that's going to be important when we talk about our new term called impulse. One way you can think about impulse is it's the product of the average force of an object and the time interval over which it acts. So if you think of something getting hit, it actually is in contact for a brief amount of time, and there is a force occurring when an object is being hit. So let's go back to what Newton had said. I'm going to take the force is equal to mass times change in velocity over time from the previous section in the notes, and I'm going to rearrange that and say force times time is equal to mass times change in velocity. So I just multiplied the t over to the other side. Now this product of the force and the time, that's what impulse was equal to. So this gives us our formula for impulse. Now I don't know why the symbol for impulse is a J, but it is. So a J is going to represent impulse. And we could say that the impulse of an object can be found by multiplying force times time, or, based on what Newton had said earlier when we rearranged that, force times time is also equal to mass times change in velocity. Or, if we even substitute one more time from that previous page, this can also equal an object's change in momentum as well. Again, it's this change in momentum that's important. And when we look at an object's impulse, we can take any two of these and make an equation. So if I'm given force and time, I can find impulse by multiplying those two together. I could also find an object's impulse by multiplying its mass times its change in velocity. Or if I'm given an initial and a final momentum, I can find an impulse by subtracting the final minus the initial momentum. So we'll practice with some example problems in the next lesson, but just remember that you can equate any two of these things and make an equation. So this is kind of like a mix and match type of formula. And then there is a difference between regular P and delta P. If it's just a plain P, that's going to indicate momentum. And you want to think of that as more of an instantaneous quantity, whereas a change in momentum is actually an object's impulse, and this takes place over a period of time. We are going to have some examples to show you both types of collisions in class, and then we're also going to do some demonstrations. And one of the things that we'll talk about is why we wear seatbelts. So be prepared to kind of think about a discussion on why wearing your seatbelts is important, besides just not getting a ticket. The reason for that is we want to think about an object's impulse. Remember that impulse is equal to force times time. That was one of the things how we could find impulse. When you are in a collision, the idea is that you want to increase the collision time. And what a seatbelt does is it allows that collision time to actually increase. And if you look at the formula, your impulse is going to be the same either way. But if I can increase the time, that means I can decrease the force, and this is vice versa. Again, we're going to have some examples in class. I'm not actually going to show you a car accident with wearing a seatbelt, but we're going to do some kind of simulations so that you can see the difference between having a short collision time and a larger time of collision and see how the force is impacted. So we are going to go over this a little bit more in class. So to summarize what we learned in today's lesson, we looked at the difference between elastic and inelastic collisions. We found the formula for momentum, which was momentum is equal to an object's mass times velocity. We also related forces back to what Newton had said and looked at our change in momentum over time and how that relates to F equals ma, and we used that to come up with a formula for impulse. An impulse would be force times time, or remember that there was a difference between momentum and change in momentum. Regular momentum was more instantaneous, while an object's impulse referred to a change in momentum, so that took place over a period of time. So I hope you're ready for our first class on this chapter. We're going to have some examples with the different types of collisions, and we'll practice applying the momentum and impulse formulas.